Hello friends and welcome to this online course. So in this video we are going to see the correlation identification techniques using Python programming language. So three methods are there in statistics which are used to find the correlations. So what exactly the correlation means and how to find that with the help of Python programming language we're going to see in this video. Let's start. What do you mean by the correlation coefficients? So basically a correlation coefficient quantify the association between variables or the features of data set. These statistics are of high importance of science and technology, and Python has a great tool that we can use to calculate them. SciPy, NumPy and Pandas, these are the three common packages which we used which contain the method by which we can use these correlation coefficients fastly, effectively, comprehensively and well documented. Okay, we are going to learn the things like we are going to use the Pearson, Spearman and Kendall correlation coefficients. We are going to use SciPy, NumPy, Pandas. So all three packages can be used to perform the operation of finding the correlation coefficients. The functions are present within that. Any one of these package as per our feasibility can be chosen. Now we are going to visualize the data on regression lines and the correlation matrices with the help of matplotlib. So four packages we are going to see in this particular video. The first is scientific Python, that we need to install SciPy. Second is NumPy, then Pandas, and the fourth one is matplotlib. Okay, so what do you mean by correlation? So statistics and the data science are often concerned about relationship between two or more variables of a data set. Many algorithms, many techniques of data science we have seen in the previous video. You might have observed that. So data science and statistics are connected to each other with the help of some relationships. It's compulsory that statistics, some part of statistics or many concepts of statistics are very useful in learning the data science. So relationship between the two or more variables, that what we call features of the data set, can be found, and there are some relationships are available. Each data point in the data set is an observation and the features are the properties or attributes of those observations. Every data set that you work with uses variables and observations. So everyone, that's input. What we have inputs. So input is compulsory. Without that these ML algorithms will not work. For example, you might be interested in understanding the following things like how the height of basketball players is correlated with their shooting accuracy. Is there any relationship that they are having there? Okay, so basketball players' height and accuracy of shooting. Whether there is a relationship between employees' work, experience and salary. Okay, so salary and experience are connected together. Is that? Maybe. There are some relationships that are available. Their work and salary, obviously they are connected. Okay, they are correlated to each other. What mathematical dependence exists between the population density and the gross domestic product, that is GDP, of different countries? Is there any relationship that they carries? Obviously that they carries. So this relationship finding should be done by some proper method in the data science and machine learning. So to do this one, we are going to make use of the correlation detection and identification techniques. Now let's take an example. Okay, in previous slide I told about this. These are the name of the player, name of the employee, then years of experience and their annual salaries. We just can check it out. So the IV, okay, IV is having 10 years of experience, contains 82,000 salary, and if you contain Rob is 21 years experience, it contains 1,05,000 salary, and it's having 30 years experience, contains is having 1,20,000 salary. So in this table, each row represents one observations or the data about one employee, which are Anne, Rob, Tom and Ivy. So each column shows properties of features like name, experience and salary for all employees. So three things are mentioned there: name, experience and the salary. Now so we are going to find the correlations among these features. So which two features are correlated to each other? Now see, these are the forms of correlation we'll be getting out of here. So name is not a numerical value. So salary and experience, okay, that may be connected to each other if you plot them in the form of X and Y plot format like this. So you just can check it out. When salary increases, we are going to increase the, when experience increases, salary also increases. I'll just go back again, check this. So you can check it out. 10 years 82, 19 years 90, 21 years 15 and 30 years 120. It means that they are connected. When experience is increasing, your salary is also increasing. Okay, that's your observation. So what correlation forms we are having now? Just consider that if one factor is increasing and other is decreasing, like they are decreasing, this is what we call as strong negative correlation. Okay, so one is increasing and second is decreasing, they are inversely proportional to each other. This is what we call a negative correlation. And if you go to these blue dots, when one is increasing, second is also increasing in this direction, like this. Maybe not exactly 45-degree angle we are having, will maybe having 40-degree, 30-degree, or maybe having 80-degree also, but they are connected to each other. So it's called as positive correlation. And if they are proportionally increasing, then it's called as strong positive correlation in this format. And if there is no any effect, like x is increasing, but in that proportion y is not increasing, y is almost constant. Okay, it's just floating above one constant line, above and below of constant line. That's why it's not connected. Y is not having any effect, though x is decreasing or x is increasing. So that's what we call as weak correlations. So correlations are can be found with the help of this kind of scatter plot or the line plots. Okay, if you we have already seen this in the linear regression. One more example from SciPy I'll show here for linear regression, how to make use of this correlation technique for linear regressions. Okay, so three kind of correlations we have: strong negative, strong positive, and the weak correlation there. Remember, weak correlation is not considered while using the data, but either we have negative correlation and positive correlation. It means that there should be a strong correlation between or among the variables present. Okay, then only these variables are considered connected to each other. Now, negative correlation, that red dots which you have seen, the y values decrease to x increases, weak, no effect, and positive, when x increases, y also increases proportionally. Okay, so that's what we have seen already in this end. And now in our table, we just can check it out. I have plotted all of this. So on x-axis, I have years of experience, started from 10 to 30. Okay, and on y side, I'm having salary in thousands. Okay, from 80k to 120k. Like, and when I plotted that, we just can check it out. When x increases, y also increases, but not exactly 100% proportion. This proportion is there, but not exactly 100%. They are having positive correlation to each other, and if you plot that, it will be something somewhat linear. Okay, in this way, that's why we can conclude that now salary and experience of the person are connected to each other, and that's what we call as positive correlation in this particular table. Now let's come with the practical implementation of it. I am going to check the correlation among the variables of the data set. So there are three methods by which we can do this correlation techniques. There are several statistics that we can use to quantify the correlation. We will be learning about three correlation coefficients here. So in statistics, three commonly used correlation coefficients are used. Okay, first is Pearson's R, then Spearman's rho. Okay, so rho is the Latin character, and the Kendall's tau. Okay, so R, rho, and tau. So these three different constants are there, the correlation factors are there, which we can use. So Spearman's correlation coefficient measures the linear correlations, while the Spearman and Kendall are used to compare the rank of the data, the importance of the data in the data set. That's what we call as rank of the data. Pearson is very straightforward. One, just like the previous example, previous plot we have seen, this is what we call as Pearson's correlation. We are directly connected to each other. So there are packages we are going to make use of: NumPy, SciPy, and Pandas. Their functions and methods we can use to calculate these coefficients, and we will be using the matplotlib as per our convenience to visualize this particular correlation in the program. Okay, so let's continue. Start with the NumPy first. So I'll go to use my NumPy package first. So let's see how exactly it's possible to use this data here. Okay, so first of all, I'll be importing the NumPy as NP. Then I'm creating one array here. So this is the array. I'm using arange function by which the array of elements from 10 to 20 are created. Okay, So that x will contain that 10 to 19 actually, so this will be last will not be considered there. Then I'll be creating one more array like y is equal to np dot array and some values in increasing order almost, only these two are not increasing, so they are created. Okay, it means that this is also in increasing order and this is also in increasing order. So x is one feature and y is another feature, just randomly I have created here. And now let's check the correlation coefficient factor here. R is equal to np dot CORF. So this is what we call as R, Pearson's R. This will tell you the strong relation between these two. So you just can check it out now. Now we have xy and xy. So this is x, y, here also x and y. So x to x, okay, they are 100% connected. That's what is showing 1, and y to y, they are connected 100%. But the correlation between x and y is this one, 75%. Okay, it means that we can expect deviation in the output when input is changing. Okay, and that probability is 75%. So 75% deviation will be there if you are changing the input. If you are changing x, y will also change by 75%. Okay, that's what we are going to make use of the Pearson's R coefficient. Okay, and if I want to separate them, so this matrix is created, 2 by 2 matrix. Depending upon the number of features that we are going to use, this matrix is formed. Okay, if I want to use the 0 to 1, 0 to 1 means x and y are connected to each other and y and x are connected to each other. So they are same. No much changes are there. No changes are there actually in the relation between them. So the correlation between x and y is 75.86% there. Okay, so this is the way by which we can create the coefficient factors. Okay, so we have seen this one already here. This is the actual matrix that we expect from this. Okay, it's generated here, but actual matrix is like this. Okay, the values on the main diagonal of correlation matrix, upper left and lower right, are equal to 1. Remember, upper left and lower right. The upper left value correspond to correlation coefficient for x and x, and lower right is obviously y and y. That's why they are equal to 1. That's why we usually need the lower left and the upper right values of the correlation matrix here. These values are equal and both represent the Pearson correlation coefficient for x and y. In this case, we are almost having 0.76, means 76%. These x and y are correlated to each other. Okay. Now, same task we can do with the help of the SciPy also. So if you are going to make use of the SciPy, so let's check this one. So here in it, so NumPy I am using and I am importing scipy.stats. So inside the scientific Python package, we are going to have one sub package called as stats. Inside the stats, we are going to have multiple different functions by which we can calculate this particular factor. So let's arrange. Same example I am taking here also. np.arrange, okay, a range that is 20 to 20, and the second array is this, like, okay. So I'll just created it, and now first of all, let's see Pearson's R coefficient. Okay, so here scipy.stats.pearson r xy. Okay, so these two parameters I am passing, and I'll be getting almost same values, exact same values there. They are connected. I'm not going to have this value in the array format or matrix format. I'm having these values into the tuple format. Okay, out of which the first factor which is shown over here is the coefficient, or is the correlation coefficient for Pearson generated by the SciPy functions. Okay, which we can see here with the help of this particular method. Okay, by using SciPy we can make use of this, and if we want to go ahead of using other constants also, that's also possible by this method. So let's see this one. So if you want to see the Spearman's R, so row, that is Spearman's row that we call. So function is this Spearman's row, scipy.stat.spearman's R x and y. So Spearman's row is this, and it contains a p value there also. See, the correlation is almost 97.57%. This is given by the Spearman, and if you are going to use the Kendall's tau, it is 91.11%, and its p value is 2.97 something. Okay, if I want to separate these particular values there, so we can make use of the Spearman R, X, Y and 0. 0th value means exact constant I'll be getting. Okay. And for Spearman's R, if you want to use the correlation factor exactly, so I'll be making use of this method. SciPy dot stats dot Spearman R XY dot correlations. Okay, so whatever output generated by this, I'm taking correlation only out of it. Okay, same case for Kendall star also. Check this. Or one more method I can use, I can separate these two constants in R and P value format also. So I can use, say this one. We know that function can return two values from Python functions, and they can be stored separately also in two different variables, R and P. Okay, so they are stored there, and now see R, P value, they are separated. So this is the way by which we can make use with the help of SciPy. And same task we can do with the help of pandas also. I'll go to pandas now. See, I'm importing pandas as PD, and in case of pandas, a sequence of the sequence, any kind of sequence, is basically stored in the form of a series object. Okay, as we know, series. So here I'm going to make use of the series object there. So you can check it. X is equal to PD dot series range. Okay, and another series which I have formed here, Y. Same values I am taking there, and here if I want to use the Pearson's R, so Pearson's R is created by using Y dot CORR, means Y correlated with X, or I can use X dot CORR also. Okay, 75.86%. So here I am making use of the series objects. So two sequence objects, they are connected. So basically when you import a data set, so that data set is imported in the form of a data frame, and every individual column of the data frame is a series, and their connectivity we can find with the help of pandas. So pandas is very useful, very effective package for such kind of the things, to find the correlations among the different kind of the features. Okay, and if I want to change the correlation functions here, so I am using Pearson's R by default. If you want to use Spearman's rho, so I'll make use of X dot CORR Y. So X correlated with Y by this method, Spearman method. So check this, it is 97.57%. By Kendall's method, 0.91, that is 91.11%. So this is the way by which we can find the factor of correlations with the help of different functions in the from the statistics here, the pandas we have seen. Okay, so let's come with the most important topic here, that's which we call as the linear correlation. The linear correlation measures the proximity of mathematical relationship between variables or data set features to linear functions. Okay, so they are linear functions, they are connected to each other with the help of a linear functions. If relationship between the two features is closer to some linear function, then their linear correlation is stronger, and absolute value of the correlation coefficient will be higher. Okay, now what do you mean by the Pearson correlation? So consider data set with two features, X and Y. Each feature has n values, so X and Y will be the n number of tuples. Say that the first value X1 from X correspond to the first value Y1 from Y. Okay, they are just connected, like salary and experience consider. The second value X2 from X and second value of Y2 from Y, and so on. So they are connected. Then there are n number of pairs will be created, like X1 Y1, X2 Y2, X3 Y3, X4 Y4, and till Xn Yn. So each of this XY pair represent a single observation. So such n number of rows or n number of observations will be present into the data set. Okay, now how Pearson correlation actually works? So Pearson correlation, Pearson product moment correlation, is a coefficient, is a measure of linear relationship between the two features. It's the ratio of covariance of X and Y of the product of their standard deviations. Okay, it's often denoted with the letter R and called Pearson's R. So we can express this value mathematically with the equation. Yes, check out the equation. With the help of this equation, this R is calculated. So exact percentage of collinearity is found with the help of the Pearson correlation. Okay, so when they are almost linearly connected or 100% connected, it will give one correlation. But if they are not 100% connected, they will go with some 0.9, 0.8, 0.7, when the collinearity when the covariance decreases, in that case we'll getting this value less than the least. Okay, this is Pearson correlation. So the Pearson correlation coefficient can take on any real value in the range -1 to 1. Okay, so any value can also be present there. The maximum value R corresponds to the case where there is a perfect positive relation between x and y is there. Perfect. So as x is 1, y is 10, x is 2, y is 20, x is 3, y is 30. Perfect linear is present. Okay. In other words, the large x value corresponds to the larger y value and vice versa. Okay. So when value of R is greater than 0, indicate that positive correlation is there for x and y. When value R equal to 0, then that case x and y are independent, perfectly independent of each other. They don't have any relationship between them. And if value of R is less than 0, indicate that they are having negative correlation between x and y. Okay, so negativity and positivity both can be found with the help of the Pearson correlation. Okay, so this value must get approached towards 1 or -1. Okay, so 1 will give positive, -1 will give negative. But if it is approaching towards 0, independence of the features increases. Okay, so minimal value -1 correspond to the case where there is a perfect negative relationship between x and y. In other words, larger x value correspond to the smaller y values and vice versa. This is what we call as Pearson's correlation, which I have talked about, just summarized over here in this particular presentation. Equal to 1 perfect positive, greater than 0 positive, equal to 0 independence, less than 0 negative, and equal to -1 perfect negative linear relationship is present between x and y. Okay, so this is what your conclusions are from the Pearson correlation factors. Now linearly, so remember why I just focus on this particular correlation much, because most of the time data sets are having finding dependency by using this Pearson correlation. Pearson correlation, exactly percentage of deviations are given by them. Okay, so negative, positive, this we can find with the help of the Pearson's R. That's why it's very useful. Now let's see an example of linear regression here. The linear regression is the process of finding the linear function that is close as possible to the actual relationship between features. We have already seen this particular concept as the first example of machine learning. Okay, so it's very easy for us to identify here. In other words, we determine the linear function that best describes the association between the features. This linear function is also called a regression line, and we can implement this regression line with the help of SciPy. We'll get linear function that best approximate the relationship between two arrays as well as the Pearson correlation coefficients. Now let's see how to create that linear regression here. Now let's check it out. So first of all, I'll just make use of the same values here in the linear regression 10 to 20 and some more factors present there. Check this one. Okay, I just imported, and now I want to create the linear regression line. So inside the scipy.stats, I'm having one more function called as lean regress. With the help of this lean regress function, linear regression relationship between x and y can be found. Linear regression class is also present that we already seen in the scikit-learn package. Similar task will be done by will be controlled by the lean regress function here. So just check it out. It will return a result, and that result contains all the factors that linear regression must be having. Like linear regression contains two things, that is what we call, see for example, if I consider this data set, I'll just write the function here. Y, its output variable, is equal to ax, or let's have mx plus c. So for this case, what we have, m is what we call as m is the slope. Okay, so m is the slope of the line, and c is called as intercept of the line. Okay, so if I want to store the if I want to print the slope, so check it out, just a minute, so put it in comment. Okay, so slope is 7.43. the line which were drawn contains a slope like this, and its intercept is this -85 as the intercept that this line contains. So based on this particular formula of line, these values are calculated by linear regression functions. Okay, along with that we will having R value and P value also. See this one. So R value is the relationship of Spearman's R 75, okay, which you can find, and if you want to use standard error, it is 2.25. standard error is present there. Okay, so by this way you can just make use of linear regression. I'll just check it out whether these values changes when you change the values there or not. For example, 214 I'm just making use here. So this is perfectly linear, but this is not perfectly linear. I will just make use of it 3 here. Okay, now it is continuously increasing. So let's change this. Okay, slope has changed, it's also changed. Okay, so R value is also changed, 0.7537 something. Okay, P value is also changed. So it depends upon the values which we use over here. These values are intended to get changed. Okay, so this is the way by which we perform the linear regression operations over here. Now if I want to make use of this same technique with the help of the two-dimensional array, that is also possible. So what I have done over here, here I just added all these values in two-dimensional arrays. You can check it out. This two-dimensional array I have created. The tasks which are done above, same we can do with the help of the two-dimensional array also. So let's check it. Xy is equal to np.array, and all of these values 10 to 19, 10 values are there, and remaining values I put over here. Okay, so it's a two-dimensional array which we have created. I'll just show you here. Okay, a 2D array which is present 2 rows and 10 columns. And now let's create a linear regression function for this. Now when we use in this way, so this a complete tuple is a linear regressor result is stored. Okay, and you can check all of these output at once. I'm not storing this value in any variable which was stored previously, but here see slope, intercept, R value, P value, standard error. So all of these are generated, and you can find them here on the screen. Okay, so this is the way by which we can perform the linear regression. Okay, and one more, if you are going to make use of this with the help of T. So okay, let's check this output. T means transpose of the array. So transpose, I have done the transpose. So by this transpose, I have converted X as output and Y as input. So your input and output are swapped now. Okay, so by using this transpose also you can create a linear regression. So check it out, x scipy dot stat dot linear regress xy dot t. Now this is done. After transposing, check after transposing, is there any change in the output or not? Again, no changes. See, almost what we are having R value here. So R value is 0.7586. Here also it is same, and all other values, slope and intercept, they are also same. Okay, so they will not be changed because relationship is same. Relationship is not changing, though if you change their deviations from input to output or output to input, that we already seen Spearman's R. Okay, so if you consider how X is connected to Y or how Y is connected to X, they are same. That's why their output is not exactly changing over here. Okay, so this is how we can make use of the regression lines here. Now if I want to work on the multidimensional data, okay, we already we have seen this one, but sorry, we have seen this for linear regression, but if you want to perform the similar kind of operation on multidimensional data to find the correlations, so let's see how to do this one. Okay, so go for the NumPy. Now here I'll be making use of the multidimensional data set. Multidimensional data means I am having now two inputs, okay, two columns, and on that two columns or three columns I want to find the correlation factors. So starting with the NumPy first. Previously we have seen X and Y separately, and now consider X and Y both are stored into the same array. Then what will be happen? So let's see, xy is equal to np.array, and here the first column is this, second column is this, first row is this, second row is this. Okay, they are stored into it. I'll just execute this, and now let's see the correlation factor. So again, from NumPy CORR COEF, this function will show you the correlation between the first row and the second row. So again XX is this, YY is this, XY is this, YX is this, in this way. So if they are separated or if they are same, then also your correlation function will work. Okay, and if you're passing single parameter, it must have multiple different features as input present over there. So if you are having a data set, like I'll go to pandas. In pandas also the same thing are possible. Generally we don't use numpy for this, we use pandas, because pandas will work on data frame directly for this case. Now let's see, I'll add one more parameter there, that is the 3 x, y and z also. So we are having first is x, second is y and third is z. Now let's have relationship between x to y, y to x, or x to z. Check it out. Now see, this is your correlations. Now we can find this one. This is 1 1 1 diagonal values, because x x, y y, z z will be 1. Now x and y, this is what we are already achieved. And now x and z, see this one, x and z are connected to each other 96%, but negatively. X and z, this is x, this is your z. You can check it out. These values are negatively incrementing, it is decrementing, and these values are incrementing. So these and these are connected to each other negatively 96%. Like x and y, 96% relationship is present there, but they are negative relationship. And if you go to y and x, means this is y and this is x, so it is 83%, again negative, because if you see the z is negatively incrementing, that is, it's decrementing there. That's why relationship between the x and z or y and z is always negative. So it's 83% y and z and 96% between x and z. Okay, so this is how we can make use of the multi-dimensional data set also. If you are having more number of columns, more number of, we are having a n by n matrix, their relationship, their correlation can also be found with the help of the function COERR COEF. Okay, so this is how we can do with the help of numpy. And if you are going to do the same thing by using scipy, that's also possible. Okay, by scipy also we can perform the similar kind of operations there. Okay, so check this out. We're going to make use of I'll show you this one when we are going to see the similar operations. So first of all, try to use the same thing by using pandas. Okay, as I told about the pandas is very regularly used in data science and machine learning applications. So there we are going to make use of this. Okay, so let's see how to use it. So let's see, I'm going to create the first series object, that is x pd.series from 10 to 20. So let's run this. X is created. Second series object is created y, which values are same as we have seen in the previous example. And third is z, this value is same that we have used in the numpy, which is negatively increment, that is decrementing. And now what I'm going to do here, I'm going to make use of a data frame of x and y together. Okay, as we know, from series we can form a data frame like this, pd.data frame. These are the x values which all x are stored, and y values where all the y values are stored. Okay, let's create this and check the correlations between them. So we got a data frame where the correlation between x and y are shown in a table, in a data frame format. Okay, and now if I combine the z also along with it. Okay, if I'm combining a z, so see this one here, x values, y values, z values. So 3 columns now I'm creating to the x, y, z. If I print this x, y, z here, see this is what we are having, a data frame. So generally in a data science application or machine learning applications, we read the data from CSV file, and this data will be stored in this format, in a data frame format like this. Okay, and after that, if you want to find a correlation, which two factors are connected to each other, okay, that we can find by the COERF method here. Okay, so COERR. So let's see. Similar output that we have seen in numpy, we can achieve with the help of the pandas also. See this one, 96, negative 96, this is negative 83%. Okay, so here the advantage is that we are having the column names and the row names also. So it's very easy to do the same operation with the help of the pandas. So pandas can do this operation also to find the Pearson's R. Okay, so this is how we can achieve these particular operations here. Okay, So even we can store that value in the matrix format also. Okay, you can store that in the matrix format also, like this. Okay, COER, like I'll just execute this, see, like this. So this matrix we can make use of COER matrix xy dot COERR, and the correlation matrix generated we can store in a variable, and if you want to access that, I can access like this. Okay, matrix at x values, y values. Okay, so x and y, where x from this side, that is, sorry, x from row and y from column. Okay, y from column, that we can find this value I am getting over here. Or I can use index at also. This method will show you 0 and 1, 0 number row and column number 1. So same value is present over there. Or if I want to find correlation of xy with z, that also we can make use of. See this one, x and xy with z means x is correlated with z 96% negatively, and y is correlated with z 83% negatively. Okay, like, so they are connected to each other. So we'll have a deviation in x and y, sorry, x and z, when they are changing 96%, and deviation in y and z for 83%, like this. And same operation we can achieve if you want to use Spearman's R. So Spearman is this. Okay, second Spearman correlation, check it out. So Spearman's correlations are, so x and z are connected to each other. Okay, and this is Spearman's. Now Kendall's, this is Kendall. Okay, check it out. This is Kendall's constants generated there. So Kendall and Spearman are showing x and z are negatively 100%, they are connected there. Okay, they are using rank data actually, and based on this rank data, the outputs are shown on the screen. Okay, this is how we generated the outputs. Like if you want to use correlation with others, two with others, so to find the output variable in the data set, this method is very effective. This method is very effective. So if you want to find the output variable, means which is your dependent variable, which variable is getting deviations much when one of the input changes or more than one input changes. So CORR with this function is very useful to find such kind of the correlations here. Okay, now this is what we have talked about, the Pearson's correlations, which is linear, straightforward. Now the others two, that is what we have, the Spearman's row and Kendall's tau. These two are working on the rank correlations. What do you mean by rank correlation? So rank correlation compare the rank of the ordering of the data to related to two variables or the data set features. If the orderings are similar, then correlation is strong, positive and high. However, if the orderings are close to reversed, then correlation is strong, negative and low. Okay, just inverse to that. Or I'm just talking about ordering, not the relationship. In other words, rank correlation is concerned only with the order of values, not with the particular value in the data set. Okay, so when the ranks means when the order is almost same, x and y containing similar order of increment, then increment or decrement, then this value whatever we are having, the row or the row value basically, will approach towards positively 1 or negatively -1. Remember, see this one, how rank correlation is identified. The left plot, this one, okay, perfect positive linear relationship between x and y, so r is equal to 1 for this case. The center plot, this one, positive correlation is present. Okay, positive correlation is there. And the right one, this one, is containing negative correlation. However, the linear function is not there. So this is not perfectly linear. This is also not perfectly linear. But positive and negativity is present over there. They are having some function by which their deviations are possible over there. So for this case, R will be different for both of these cases. Okay. So when you look at only the ordering or the rank of this relationship are perfect. The left and the central plot, the left and center plots show the observations where larger x value always correspond to the larger y. Okay, larger x and larger y. This is the perfect positive rank correlation, and the right plot illustrates the opposite case, which is perfect negative rank correlation. Okay, negative rank correlation. So this is, we just consider it, it's incrementing in all the cases. Highest and lowest are matching, and increment is also matching but not linear. Here a most negative or opposite cases present over, this is what we call as the negative rank correlation present over there. Now, so this is basically what we call as rank correlation, and in rank correlation again two different methods are used. The first method is the Spearman correlation. The Spearman correlation coefficient between two features is the Pearson correlation coefficient between their rank values. Perfectly linear, incrementing, both are incrementing in the same direction, no deviations. That's what we have, Spearman correlations. Calculated means proportionality is not expected, ordering is expected. They are incrementing means incrementing. Okay, if one is decrementing in between and its deviation is present, so Spearman's rho will change. Okay, it's calculated the same way, the Pearson correlation coefficient, but takes account their rank instead of their values. Okay, and often denoted by the Greek letter rho. This one is called as Spearman's rho. So say that we have n two tuples x and y, where x1 y1 go on x2 y2 something. Observations pair of corresponding values are present there. So we can calculate the Spearman correlation coefficient rho the same way the Pearson coefficient will also use the rank instead of the actual values from x and y. See, so it can take a real values in the range -1 to +1, where maximum value of rho 1 correspond to the case where monotonically increasing function is there in between x and y. Okay, exactly 1 increasing, they are increasing. Okay, in other words, large x value correspond to the larger y value and vice versa. Okay, the minimum value rho equal to -1 corresponds to the case where there is a monotonically decreasing function present in x and y. In other words, larger x value correspond to the smaller y value and vice versa. This is what perfectly Spearman correlation is present there. I'll just go above and check it out. Now see this. So the Spearman correlation between x and y, so this one x and z, sorry, x and z, it is perfectly negative, perfectly negative. So you just can check it out. I'll just go to check the values now, and let's focus on that. Okay, this one. Okay, so see this one. This is perfectly incrementing, correct? And just inverse to that, this is perfectly decrementing. See this, perfectly decrementing. So their ordering is same. There is no any deviations present over there. That's why their relationship is, according to Spearman's formula, is negative, -1. Okay, getting this. And if you consider y and z, check, this is incrementing, but not perfectly. So it is decrementing one time and then again incrementing, decrementing one time and then incrementing, and here it's completely decrementing. So if you consider y and z, the one deviation is present there. So if you go to y and z for Spearman, y and z, it is 97%. Okay, sorry, not this, this is negative 97%, and same case is there between x and y also. Both are positive, but only single deviation is present there. That's why it is 97%. Here also, this is incrementing, this is decrementing, but only one deviation is present there. That's why it is 97% decrementing. This is what we call a Spearman. Okay, according to the rank, this correlation is identified, and wherever required, means they are not linear. Based on ordering, this identified. So when we require, Spearman correlation coefficient can also be considered there. And now let's focus on the third, that is Kendall's correlation coefficient. So Kendall, let's start again with two tuples x1 y1 x2 y2, like we are having many observations. Okay, it's somewhat complicated, but okay, xi yi xj yj, like where I is less than j, and one of the three things are present over there. Which one? So concordant, if either x of I less than x of j and y of I greater than y of j, or x of I is less than x of j and y of I is less than y of j. Okay, first one concordant. Second is discordant. Discordant means x of I less than x of j and y of I is greater than y of j, or x of I is greater than x of j and y of I is less than y of j. So we are talking about these two only, x and y, and their pair of observations. Now, neither if there is a tie, x of I equal to x of j, or tie in y, y of I is equal to y of j. The Kendall's correlation coefficient compare the number of concordant and discordant pair of data. Getting this? Number of concordant and discordant pair of data. So, a one observation with other, again one observation with other. Okay. So, if I am getting this value as concordant, or if I am getting this value as a discordant, okay, and none of them, if values there is a tie in between these, then this value will be discarded. Okay. So, focus on that. Just when you are comparing to any one of these two, so first, second, third, fourth, fifth, second, like this, but make sure that I is less than j. Okay, so in this way Kendall's correlation finds concordant and discordant. Now, this coefficient is based on the difference in the count of concordant and discordant pairs related to the number of xy pairs, and it's often denoted with the letter tau. It's called as Kendall's tau. So how many percentage of difference is there between concordant and discordant? That is Kendall's tau. Remember this. Now, let's take an example. It can take a real value range, again -1 to +1, and maximum value is 1, correspond to the case where rank of corresponding values in x and y are the same. In other words, all pairs are concordant. Getting this? All pairs are concordant. In that case, we are going to have tau equal to 1, and minimum when tau equal to -1 correspond to all the cases rankings x and y reverse of ranking in y. In other words, all the pairs are discordant. That is what we are having Kendall's concept. And if you are having 50-50, 50% concordant, 50% discordant, then tau will be 0. Okay, or we are all they are same. In that case also tau will be 0. This way your Kendall's tau is calculated. That's it. So let's go for finding this particular method with the help of a SciPy correlation. So check it out. So I'm going to make use of a function rank data here. With the help of the rank data function, I'm going to show you the ranks. So check it out. The rank ordering perfectly linear. Now check this one. This is not perfectly linear. What do you think? So see, this is the lowest value present at first index, highest value as the last index in case of x. But in case of y, it's not the case. Y contain this value lowest. See, 1, then 2, and then 3, 4, 5, 6, 7. This way. Consider z. What's the problem? Z is not defined. Oh, yes. Now check this one. Lowest value is here and highest value is here. So their rank is perfectly decrementing. Correct? And now check it out. So just focus. What's the rank that this may carry? This one. So for example, this is in this case we are having this rank 1 and they are same now 2. Okay, sorry, 0 rank 1, then 2, 3, 4. Say this one 2, 3. So 2, 3. What they have done? 2.5, 2.5. 2 plus 3 divided by 2. So their ranks are same, 2.5, 2.5. So this is first rank, this is 2.5, 2.5, and this is the fourth rank. So in this way these ranks are identified, and if you are having some not a number values in that, see this one np.nan. So nan is considered as the highest value there, okay, containing an highest value. And if you apply the arc sort into it, take this one, arc sort of y. So we sorted this plus 1, and check it out how to find the tau. This is the Kendall's tau. It is 91% connected there. Their correlation is 91%, and if you want to separate them, you can separate by the same method. SciPy.stat.Kendall's tau x. So tau will be present and p value will be present here. Okay, and tau I can identify. The similar operations we can go ahead by using the SciPy function also here. Okay, tau, and then use this and check the correlation matrix now in this way. Okay, so Kendall's coefficient is identified by this particular method with the help of the SciPy correlation factors. Okay, so whatever I shown over there by using scipy.stats.kendall give the parameters, and Kendall can be found with the help of this particular function here. In case of 2D also same operations I can make use of. Here one function I have made, round of decimals 2 means I'll be getting these values, but I'll round my values towards 2 points after the decimal point only. Okay, so in this way we are going to make use of the Kendall's top. Okay, so check it out, all these Spearman's R we can find with the help of scipy stats Spearman R function, but generally we basically focus on the pandas. So let's go for the pandas and check this one. Okay, so Spearman and Kendall also we got. So this one Kendall and Kendall with others is also similar. See, they are perfectly connected here, y, x and z, but here we have 91%. Okay, so discordant and concordants are exactly not matching over there, that's why it's calling 91%. They're connected, but only 91% as per the Kendall's formula for finding Kendall's there. Now visualization of regression lines. So it's very easy, we already seen that in linear regression function. I'll just show you how to make use of this linear regression here. Okay, so I'm importing the matplotlib.pyplot first, then creating the subplots, plt.subplots, and then let's have a plot x, y, line width, marker, label data points, and then again I am plotting x, then the as per the function, what function is generated, intercept in plus slope into x, label will contain line, then set label I will have x side x label, y side y label, and then the legend face equal to white color. Okay, so let's do this one. Similar operations I just added, which was in the linear regression, and check this one out. Matplotlib, so subplots I got 1 and 2. Then these are the original points. Okay, original points, and this one is your line which you have plotted, regression line. This is printed by this method, regression line, face color is white, and check the output of it. So this is regression line on which we are expecting it. This is somewhat outlier. If you make it close to it, so line deviation will be there, and we'll get more accuracy in this particular case. This is how regression line is possible. Similar method we can achieve with the help of scikit-learn also, and we can get the prediction of the output. Okay, so this is how we are going to make use of the different correlation methods available in the scipy function, scipy package, numpy package, and the pandas package. So I'll just summarize it. Whenever a data set comes to you, in that you have to find the factors which are depending on each other. You have to find the input variables, you have to find the output variables. In that case, it's very useful to find a correlation among all of this. And when you're going to find the correlation either by using Spearman's R or by Pearson's R, Spearman's rho, or the Kendall's tau, we can easily find which factors are connected to each other. So we'll decide which can be your input values or which can be your output values. Okay, so this is the method by which you can find the correlation things. So you are open to use these particular programs, and if you have any doubts, the communication methods are present there on your screen. Thank you. Thanks a lot.